In this video I will look at the dynamic range of 6 different receivers. One of them is the Perseus, and right now I have a signal generator connected directly to the Perseus. It's this one, and it's set to -80 dBm. And the Perseus S meter tells me that the level is -80.6. So this is within 1 dB, and I think I'm happy with that. But just to check, I check another signal generator, this one. And then what I see on the Perseus screen is -80.4. So the generators are similar, although they are promised ±1 dB, and the Perseus is within 0.5 dB from that. So I think the levels are accurate enough for what I'm going to do. I have now connected the signal generator to the spectrum analyzer, and here I can read that the level is -79.9, and the other generator is of course a little different. It is -79.5 or 0.6 or 7. Well, so this is within 1 dB from the other measurements. So I'm happy with the instruments, the accuracy of the calibration. I will not take anything into account to compensate for the small differences I see. Here is the setup. I have an antenna and a low-pass filter at 30 MHz. That's to protect the wideband amplifier, the PSA 45043, from the local FM band where there are strong signals. Then there is one more amplifier with the same MMIC. Then a stepped attenuator, so I can reduce the antenna signal here. And then there is a hybrid to combine this antenna signal with a signal that comes from 3 signal generators that are summed in a power combiner. It's a hybrid from mini circuits. Then there is a stepped attenuator here, so I can conveniently change the level of all the generators at the same time. So this signal generator group is combined with the antenna signal in this hybrid combiner, and the output is run through an MGA 3689. It's an MMIC with 13 dB gain. And then there is an amplifier with a power MOSFET, BUK 75150. And then there is again a stepped attenuator. And the signal goes then here to another BUK 75150, followed by a 3 dB attenuator. Because then there is a notch filter, and the notch filter has a 50 ohm impedance, but not on the notch where it is a short circuit. So this 3 dB attenuator is to protect this amplifier from looking into a short circuit. That's on the notch frequency where there is not going to be any strong signals, but anyway. On the output of the notch filter there is a 6 dB attenuator, because it's followed by a coupler which just picks up some of the signal, but more importantly, another couple, but the 6-port Wilkingson splitter needs a 50 ohm source impedance generated by this attenuator, because otherwise it wouldn't isolate between the outputs. So the signal here, which is the sum of the signal generators and the antenna signal, but not at the notch frequency, because then there nothing comes through. The 9 dB coupler is followed by a 5 dB attenuator, and that makes the spectrum analyzer show the same level as I'm seeing in the Perseus, which has a 6 dB attenuator on one of the Wilkingson splitter output ports. Then there is a minus 20 dB coupler, by means of which I can send a signal at the center of the notch from this generator. So this pilot tone from this generator is used to compare with the noise floor that the receivers see. The next step is to set attenuators for all these receivers: the Airspy plus the Spyverter, the HF plus from Airspy, the HF plus Discovery from Airspy, the SDRplay RSP1, and the AFEDRI-Net, the network AFEDRI. So they all need different attenuators in order to make the same signal-to-noise ratio on the audio output of all these receivers. Because I'm looking for the dynamic range, not sensitivity or so. So the assumption is that the user is clever enough to add attenuators or amplifiers as required to place the noise floor at the level where the external noise floor lifts the radio noise floor by maybe 10 decibels or what the operator finds suitable. So that is for this test. It's the dynamic range, not the performance you see when you just plug the radio into an antenna. I have now corrected this schematic diagram. After the notch filter and the 6 dB attenuator, first comes the coupler of minus 20 dB that I used to inject the signal, and then the 9 dB coupler to bring the signal out to the spectrum analyzer. And now I see the same level here and here. This is the signal at the center of the notch. I have to set minus 44.5 dBm to read on the Perseus. I think it is visible. Minus 80.5. And then on the spectrum analyzer I read minus 80. So now I read the same on the spectrum analyzer as I do on the Perseus. Means that I can look here for whatever is going into all the receivers. And it's calibrated to agree with the Perseus. I have set a much lower signal level, minus 113 dBm according to the Perseus. And I am looking at the audio output from the Perseus with this instance of Linrod that is set in signal-to-noise evaluation mode. The yellow track here is the signal-to-noise ratio measured as the signal level within this narrow passband compared to all the noise in the wider passband. It is close to 2 kilohertz, and the entire band here is protected by the notch filter. So when I evaluate the signal-to-noise ratio here, I read 0.0. Well, I calibrated it to show 0 for the Perseus. I have switched off the Perseus and enabled the HF Plus Discovery with these settings. And as you can see here, the bandwidth is very similar. The signal level is similar, and signal to noise ratio has gone up a little bit. So I can read that out like this. And I see 0.3 dB. Now I have stopped the Discovery and started the RSP1, and you can see parameters here. I'm running with AGC. And here you can see what happened. The signal to noise ratio is a little bit below Perseus, not much. And the IF filtering is very similar. So I check what is this signal to noise ratio. Oops. I thought I had fixed this. Well, minus 0.1. Now I've stopped the RSP1 and started the Spyverter Airspy combination. And here is the settings. And here you can see signal level went up just a little. Signal to noise ratio is similar. I will read it out. Hopefully this is successful now. And I see minus 0.2 dB. Now I stopped the Airspy Spyverter combo and instead started the HF Plus, the old one with 2 antenna connectors. And here are the settings. And I will read the signal to noise ratio from here to here. Plus 0.3. And the filters are the same all the time. I have stopped the HF Plus and started the Net AFEDRI. And you can see here there is a small change of the signal to noise ratio. I don't have 0.1 dB stepped attenuators, so I cannot set levels so exactly. But this doesn't matter, the errors is small and I can correct for them. What I see here is 0. And the filter is very similar to the other filters. I have increased now the signal level with 40 decibels. And I will use the spectrum analyzer to measure what goes into all the different receivers, the antenna connectors of the receivers. Here is what goes into the Perseus, minus 73.8. And here is what goes into the AFEDRI, minus 83.8. And here is what goes into the Discovery, minus 88.4. And here is the HF Plus, minus 89, once more, minus 89.3. It's a little bit unstable because we are approaching the noise floor of the spectrum analyzer. So I have to look a couple of more times. Well, minus 89.5. And this is what goes into the Spyverter, minus 71.5. Note how stable it is now when the signal is strong. minus 71.6 maybe. And finally, this is the RSP1, minus 83.9. Yeah. I have connected this noise source to the input of the AFEDRI, and here is the S meter, and I read out, and as you can see I calibrated it to show 0. And then I switch on the noise source, and it's now set to 9.8 dB noise figure. And I wait a little while until I can read what the new noise level is. And I read here, and it shows 3.05. And I wanted a 3 dB increase, and this is accurate enough. So the noise figure of the AFEDRI is 9.8 dB. Knowing the relation between the different power levels that enter the radios and the signal-to-noise ratio on the audio output, I can compute the signal-to-noise ratio at the antenna connector of the radio, because these different power levels tell me what attenuation was, and then I have to correct for what the actual signal-to-noise ratio was. Now, I know the noise figure of the AFEDRI is 9.8 dB, so I can compute the noise figure of all the other radios that range from 22 for the Spyverter plus the Airspy. This is reasonable for an HF receiver below, let's say, 14 megahertz. Above that, one would need a preamplifier. And then the HF plus, the noise figure is too low, so an attenuator is probably a good idea for this. But maybe it isn't needed. Well, it is needed for the HF plus because it is blocked by AGC on the medium waves. The Discovery is protected by filters. And I can of course also compute what are the actual attenuator values that I have inserted, and you'll find them here. I will now inject a strong signal 20 kilohertz below the frequency of the weak signal, means the frequency of the notch. And I'm listening now to the RSP1, the SDRplay, and here is what it looks like. And then I switch on this strong signal, and we can see that the AGC acts, and signal-to-noise ratio is degraded by 5 dB, so the signal is so strong, too strong. I reduce it by a couple of dB. That was too much, 1 dB more. Oh, there is some hysteresis here, 1 dB more. Well, this is roughly what I need to degrade this radio by 3 dB by AGC action. The signal level I had to apply was minus 57 dBm. Here is the Airspy with the Spyverter, and here's the evaluation of the audio, and I switch in a strong signal like that, and the loss of signal to noise ratio is close to 3 decibels. And for that, the signal level I have to inject is minus 44 dBm. Here is the Airspy Discovery, and I turn on the strong signal. And you can see the noise floor goes down. It goes from 10 to minus 2, while the signal to noise ratio is degraded by 3 decibels. Probably something could be done to the firmware or maybe the software in SDR Sharp, or perhaps both of them, to keep the gain constant for the noise floor. Because this isn't really pleasant when you are listening. If there is a strong signal outside the passband where you are listening, it would behave like that, and you would have to disable the AGC somehow. Anyway, the level for this is rather high. Amplitude, reference level 20, like that. Well, maybe this is minus 32 dBm. And here is the HF Plus with 2 antenna connectors, the old one. And I switch on the strong signal. And I have lost not quite 3 decibels. The signal level went down here, but the signal to noise ratio is here. So I increase the level a little bit. And this is where I lost 3 decibels signal to noise ratio, while the signal has dropped by 18 decibels. And this is what the screen looks like. So it's the same as for the Discovery. I think something should be done to the firmware or software, or maybe both. The level I send in now is minus 24 dBm. Here is the net AFEDRI. I switch on the strong signal, like that, and you can see the loss of signal to noise ratio is 3 decibels now, and the signal level is minus 18 dBm. And here is the Perseus. I turn on 1 more dB on the strong signal, and you can see it says ADC clip. So that's not acceptable, so I revert. And here the loss of signal to noise ratio is very small. I switch off the strong signal, like that. And the difference is about 1 dB. And I switch it on again. And the level, amplitude 10. The level is minus 2.2, minus 3 dBm. I have set the generator for the strong signals 1 megahertz below the center of the notch where I have the weak signal I'm listening to. And right now the SDR UNO is running on the RSP1, and the yellow track for the noise figure is close to 0, minus 0.5. And I switch on this, and here you can see the signal to noise ratio is degraded by 3 decibels, and that is for a signal at minus 30.5, 30.8. Well, so I ran the spectrum analyzer a bit slower, and I read minus 30.6 or 7 or 8 or 5. Well, minus 30.6 could be a good average for this. And now I'm running the Airspy Spyverter combo, and here is the noise floor, and then I add this strong signal to get the 3 dB SN loss. And now the level for that is minus 25.7. Now I'm running the AFEDRI, and I switch on the generator. Oh, it was on. I switched it off. And you can see off and on. I lose only 1 dB. And now I increase the signal level 1 more dB. And here something saturates the AD converter probably. So the level I can send into the AFEDRI is minus 18.5. Here is the Airspy HF Discovery. And the strong signal is not on, and I switch it on now. And you see no effect. So I turn it up slowly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15. That was 15 decibels up from some arbitrary level. And now we lost a little bit more than 3 dB, but I can continue and increase the signal. 1, 2, 3, 4, 5, 6, and here we lost much more. So I go back 1 step, and the AGC has some hysteresis, so it doesn't understand that the signal is not too strong anymore. So this happens at minus 14.5 dBm. So I reduce now the signal level. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13. And now at this point the AGC decides there is no strong signal anymore. So I get a much better than 3 dB loss. And this is at a level of minus 26.5. Now I'm running the HF Plus, the one with 2 antenna connectors, and I expect it to behave similarly. The strong signal is on, I switch it off, with very small difference in signal to noise ratio, on, and I increase the level, 2, 3, 4, 4. That gave 3 decibels loss at the signal level of minus 22.4. And I continue upwards. 1, 2, 3, 4, 5, 6, 7. Here there is a big loss, so I step 1 dB backwards. This is the strongest signal that wouldn't degrade more than 3 dB. That's minus 16.5 dBm. And I reduce the signal. And this is the point where the loss is 3 dB only. And that is minus 24.5 dBm. And finally the Perseus. It is here minus half a dB. It means there is almost no interference. I switch off the strong signal. Well, it makes no difference. And now it's on again. And I increase the level by a single dB and lose 10 dB, but there is an ADC clip. So to avoid ADC clip, I don't see any interference from the strong signal, and the level is minus 1.7 dBm. So here are the results from this test. At close range, 20 kHz, the RSP1 is 54 dB worse than the Perseus. And the Airspy plus Spyverter is 13 dB better than the RSP1. The AFEDRI is much better. The HF Plus is, well, you can read yourself. So this is a standard test, and I could do more separations, but I don't think that's very interesting. It will show differences, of course, because there are different filtering in these units. Well, I decided to do one more. This is 6 MHz separation. Means I put a strong signal on the medium wave band at 1.19 MHz. Here is the RSP1. I'm running this now, and I add the medium wave signal, and here I lose 3 dB, and I increase the level by 1 dB, 2. Now I lose more. 1, 2. Here I'm back. And that is minus 25.2. And now I'm running the Airspy Spyverter combo here. And here is the signal to noise ratio. And then I switch on the strong signal. And I set the level for a 3 dB loss. And the signal strength now is minus 18.2 dBm. And here is the AFEDRI, and the signal is on, and I switch it off. So it's only 2 decibels. I switch it on again and add 1 single dB, and I'm losing much more. So at this point, the AD converter is probably slightly saturated, and the level is then minus 17.3. And here is the old Airspy HF Plus, the one with 2 antenna connectors. And I have a signal level that affects the signal to noise ratio by a single dB. So I turn on the generator again and turn up the level by 1 dB, 2, and here we have 3 dB loss, and I continue further. 1, 2, 3, 4, 5. Here it degrades much, and I go back 1 step. So this was the strongest signal that gave a 3 dB loss, and it's, what does it say, 15.2, minus 15.2. And now I decrease the level again. Here we are back. So this is minus 21.2. And here is the Airspy Discovery. and it behaves a bit different. So I turn up the level in steps of 1 dB from here. 1, 2, and you see what happens is that the signal goes down, but the signal to noise ratio does not change much. So I lost about 1 dB in signal to noise ratio, but I lost 10 dB in signal level. And then I go 1 more dB. Well, this happens at the signal level of plus 2.3 dBm. So it's a strong signal now. I continue and add 1 more dB. And 1 more. And here the signal to noise ratio drops significant. No, it was the signal level. Signal to noise ratio is still reasonably good. And here is the point where I have lost, no, not yet. Yes, I've lost 3 decibels here. But the level is from 8.5 down to minus 4.5. So maybe something can be changed in the firmware when this problem is understood. And when I go for studies of real signals from the antenna, I will play with the adjustments of manual gain and the finer knobs on the AGC settings. This is the strongest signal I can generate with this setup. It's plus 7.5 dBm. And I'm listening to the Perseus. And I switch that signal off. Well, looking here. And the degradation is maybe half a dB, maybe less. But when the signal is on, there is a big spur. And how that's generated, I don't know. I step the frequency by 1 kilohertz upwards. 2, 3, 4, 5. And it steps by, I don't know exactly. I'm too lazy to evaluate. Because I'm not listening for spurs and things in this series of measurements. That will be when doing antennas, signals from the real antenna. Then maybe there will be unpleasant phenomena. The effect of AGC or reciprocal mixing at different frequency separations is fairly different between the radios. At close range, the RSP1 is very poor compared to the other ones, the AFEDRI, the HF Plus or the Discover, and particularly the Perseus, which is so much better. But the Spyverter is not so different from the RSP1. At 1 megahertz, things are much better because the tuners in the RSP1 or in the Spyverter have filters. The AFEDRI, it doesn't change with the frequency because it just samples the signal with an ADC without filtering in front of it. The HF Plus and the HF Discovery, they have this AGC phenomena which are rather particular. The Perseus is much better than anything else at 1 megahertz. At 6 MHz separation, the RSP1 is much more likely to create problems than the Spyverter or AFEDRI. It differs by about 10 dB. The HF Plus is similar, but the HF Plus Discovery is much better, and so is the Perseus. Really much better. I have placed these two generators close to half the frequency of the desired signal, this one, and this is in order to look for second order problems, intermodulation and overtones. So I switch those signals on, and you can hear maybe, and you can see here that the signal to noise ratio lost about 3 decibels, because here we have the sum frequency here and the second harmonic of one and of the other generator, and together they degrade signal to noise ratio by 3 dB by being equal in power to the desired signal. The AGC is acting, so the total signal level goes down a little bit here, but that doesn't affect the evaluation. The signal level, to see this, is minus 41.7. Sorry, minus, oh, it varies quite a bit, minus 40 dBm. It's two signals, so I should use a larger averaging time constant. But that's not possible with this spectrum analyzer. Here is the Airspy Discovery, and I inject those two signals like that, and the signal to noise ratio loss is now 3 decibels, and the injected signal is minus 27.7. Well, minus, it varies a little bit, but this seems to be the most popular reading. Here is the Perseus. I turn on the two signals at half the frequency, and here is a loss of signal to noise ratio of 3 decibels, and that is for a signal level of minus 27, or well, minus 27.8, or maybe minus 29. A couple of tenths of a dB is not really important in this context. What is very important is the mechanism. There are only two signals at half the frequency, nearly. But if I add one more signal, I add one at 5 MHz here, then the interference goes away, because it's caused by digital feedback. And in a normal situation with antenna signals, there will be many other signals also, and that will remove or deter those digital feedback signals. So I can increase the two tones at half the frequency, quite a lot. Here I start to see them at degrading by 3 decibels. And that is with this signal at 5 megahertz at a similar level as the other two. And the signal level into the Perseus is minus 18.7 dBm. Here is the net AFEDRI and the audio evaluation. And I bring up the signals at half the frequency. And here the SN loss is 3 decibels. But the spectrum looks rather ugly. Interesting that we don't see the expected sum and difference. We see something of higher order. And this must have something to do with the mechanism of the A to D converter. Anyway, I switch on this extra signal at 5 megahertz. And I can hear some little difference, but I don't see it in the signal to noise evaluation. So I switch it off again. And it makes some small difference. Anyway, the signal levels required to make the AFEDRI misbehave is minus 60 dBm, or maybe minus 59 rather. It's a little bit unstable because there are two signals that I'm measuring the added power of both. Here is the HF Plus, the old one with 2 antenna connectors, and I add the 2 strong signals at half the frequency, like that. And the loss of signal to noise ratio is 3 dB. And that is at a level of minus 41, minus 42, well, minus 42 dBm. Here is the Airspy plus the Spyverter, and I add the 2 signal at half the frequency, like this. Oh, that was too much. This is more appropriate. 3 dB loss of signal to noise ratio, looking like this on the screen. And the power level for that is minus 48 dBm. Maybe minus 47. I have now placed one signal at 1.2 megahertz, medium wave band, and the other at about 6 megahertz to sum up to 7, where the desired signal is. I'm listening to the Perseus, and now I switch on the signal from the 2 generators. And the sum frequency comes here, and I have lost 3 decibels. Now, I started with the best receiver, probably the Perseus, and I look here when I add the attenuator, and I still see the sum frequency at the same level. So this is not the Perseus. I have disconnected the Spyverter, and that changed radically the situation, both for the Perseus and for the HF Plus Discovery. So I will have to start with the one having most problems and then disconnecting them one by one until there is only one receiver left. Here is the Airspy Spyverter, and I switch on the two signals and lose about 3 dB. And that is at the power level of minus 49 dBm for the 6 MHz signal. Here is the HF Plus, the one with two antenna connectors, and I bring up the two tones for a loss of 3 decibels in the signal to noise ratio. And that happens at the level of minus 44 dBm. And the Spyverter is now disconnected. And here is the RSP1. And I turn on the two signals for a loss of 3 dB, signal to noise ratio. And that happens at minus 43 dBm. And here is the AFEDRI. And I turn up the level now in steps of 1 dB. 1, 2, 3, oops, 4, 5, 6, 7, 8, and you can see the irregular behavior. And I add an extra signal, this one at 5 MHz. And then I turn down from here. 1, 2, 3. So something like this with this dithering signal on. And this is minus 44, and I switch that off and make the signals weaker. And here's where it goes wrong, so this level now is safe, minus 48. So here is the Airspy Discovery, and I turn on the signals, and this other stuff is outside the notch filter, so it is various intermodulation products that doesn't matter. I have a 4 dB loss, so I have to reduce the level a little bit, well, like this maybe. So this is minus 26 dBm. And finally, here is the Perseus. And I turn on the signals for about a 3 dB loss. And all the other radios are now disconnected and replaced by dummy loads. And the level I see is minus 16. So here is a table with the second order properties I have found. And for interference with medium waves mixing with something as a second order, the Perseus is much better than anything else. But the Discovery is pretty good. The HF Plus is about 20 decibels below that, and then comes the other ones, fairly similar. So with these, a wideband antenna is not a good idea if you're close to a medium wave transmitter. There is a need for a notch filter or a high pass filter for the HF bands. I stop here and I will continue in the next video with more measurements using this setup with 6 receivers.